Good enough sync, I hope. Let's go. Stars. The thing you can barely... Stars. The thing you can barely see when you're looking up in the night sky and there's a few little white specks of light in the night sky. By definition, stars are luminous spheres of plasma held together by their own gravity. First, let's do a little test. Can you tell which one is a star and which one, by definition, is not a star? Number one, is this a star? No, because it is not a sphere and doesn't really emit light, kinda. Is this a star? Yes, because it emits light and is a sphere due to its own gravity. What about this one? Is that one a star? No, it's not a sphere. Stars emit light, we understand that, but stars emit light in very special ways. These special ways are explained in the absorption spectra. Stars are primarily made up of hydrogen and helium, as the Big Bang mostly emitted hydrogen and helium. And as we can see, we can line up a few lines from hydrogen lining up directly to the sun's absorption spectra and the wavelengths of light that the sun emits. These little black lines are the specific wavelengths of light that the sun emits. But when stars are moving, we can observe something called redshift. Say you're this little guy over here, and your local star, the sun, is moving away from you, or you're moving away from it. Right now, when the sun is not moving away from you, the light that you're seeing is orange. But when the sun starts moving away from you, it is now red. This is called redshift. The wavelength of the light gets longer, and so the light that you are observing is redshifted and looks more red than what it would be. And in other ways of light that we have observed is microwaves. The cosmic microwave background has caused a few very annoying problems for a very few nerds, but essentially was some nerds were operating a big microwave telescope, and every time they took a reading, there should be nothing out there. There's nothing happening, but they're seeing this. Just a little bit of stuff that's not noise, because it's ever present and doesn't change, but it's always there. What they were seeing was the cosmic microwave background. And this is the little section of remnant that we can see from the Big Bang, where old light from the Big Bang is now in microwaves, and we can observe it. I'm going to explain that. Essentially, what the Big Bang was, from the earliest predictions we can make and based off the measurements we see, is from the beginning of the universe itself. There's a tiny little point with a bunch of stuff in it and a bunch of energy. And so that little bunch of energy and stuff rapidly spread out and pushed away from itself. And some of the energy that was in it were gamma rays that were slowly redshifted over time and over space to become the cosmic microwave background we've already seen. And the Big Bang has pushed out a lot of stuff, mainly clouds of gas, that have formed other things. Speaking of those redshifts, from gamma rays to microwaves, we can see the cosmic expansion. Say we're the sun over here, and we're observing a nearby star through the James Webb Space Telescope. If nothing was moving, we'd be seeing orange light, right? But since we're observing redshift and space between these two things is moving away and the stars are moving away from each other, the light that we observe is redshifted and now is a longer wavelength and looks more red. Now that we know what redshift is, we should figure out what the hell is actually happening in a star. Primarily, stars are made up of protons and neutrons in a plasma form, and we'll call these hydrogen and helium when they're bonded together, helium when two protons exist with normally some neutrons. A star like our sun, our sun, is made up of primarily hydrogen and helium by weight with a little bit of other trace elements. And we can understand what happens with stars and why they emit light. But first, quarks, because they're cool, and the proton-proton chain gets even cooler when you barely understand them. Essentially, protons are made up of quarks, 3 quarks for each subatomic particle. Protons have 2 upspin quarks and 1 downspin quark, and neutrons have 1 upspin quark and 2 downspin quarks. And the spin of these quarks determine their properties, but that's way out of scope. So, we'll ignore it. And we move on to the proton-proton chain. Starting off at 2 protons or hydrogen atoms, when they collide with a lot of force and a lot of energy, they will emit a neutrino and a positron, which is literally antimatter. In this process, we'll create hydrogen with a neutron, which is known as deuterium. And then we can take our deuterium, throw another hydrogen particle at it, release a gamma ray, which is the light that we see now, just after it's brought down to visible light. And we get a helium-3 atom out of it, with 2 protons and 1 neutron. But that's not our standard helium, and we kind of want another neutron in that. So if we do the whole process again, we can take 2 helium-3 atoms and smash them together, create a helium-4, and eject 2 other hydrogen atoms in the process, which will go on to do the same thing as the rest of them did. But there are more than 2 elements. And the sun has more than 2 elements. Where did those come from? Well, same thing, but in fusion chains that are too long to explain, and in fusion chains I do not want to explain. And so, we have a bunch more elements in the universe, and these elements can be created from different stars. And now we get to explain different stars. Stars are just formed by what are called stellar nebulas, which are just bunches of mass, primarily hydrogen and helium, that condense into just the one sphere that you see normally. If there's not that much, but just enough to still form a star, you'll get a red dwarf, which will only do hydrogen to helium fusion. Then we'll run out of hydrogen, turn into a white dwarf, and that white dwarf will just emit light until it becomes a black dwarf and will sit there until the end of time. If you have a medium amount of hydrogen and helium, which is just stuff, you create a main sequence star, which keeps reacting and does reactions in its core that make more new elements and more new cool elements. And through the reactions, it will become a red giant, creating more new elements, which will eventually die, and its outer surface of the star will turn into a planetary nebula and get dispersed in the local area. The core of that star will turn into a white dwarf and follow the same process. Now, if you have even more stuff in your gas cloud that condenses, it will turn into a large main sequence star and will have even more stuff in it. Large main sequence stars will follow a path leading for them to be red giants, then for them to eventually supernova into a black hole or a neutron star. And that's all I want to explain. So that's the end.